database strategies for cloud native resilience. So we need to have the highly available database in today's environment, and we can have it with the help of Kubernetes on the cloud native environment. So I am Mayank Gupta. This is Senior R&D Engineer, Database Clustering and Cloud. I'll be your host today, and this is what we are going to cover in today's session, which is we'll talk about the database strategies, and the agenda goes around the high availability fundamentals, which will talk about the mechanisms, how to measure the fundamentals, RTO, RPO. Then we have clustering architectures, where how we can lay down all the database clusters. There are multiple strategies around it. I'll talk about it. Then for the example, I will showcase one live example, which is my SQL InnoDB cluster. I'll be talking about it, how it works in the background, how it facilitates everything within the Kubernetes cluster, Kubernetes nodes. Then we have one failover in action, how it revives itself when there is a failover on the database node or any other pod or anywhere. Then there are some DevOps concepts, like how how it works, operating it for real. So what kind of consistency, what kind of upgrades, how we can manage it for DevOps purpose. So this is what we have in today's environment. Most of the legacy applications, they have single database, and as you see in this architecture, the top blue box is for the application server, which is hard codedly connected to one SQL DB, which is only single instance. So you can see if something goes wrong with the database, then the whole server, whole DB application, and the application itself is down. There are like four major root causes that it could have frequently seen, and those are on the right, uh, red boxes. The Let's say the first one is one box, one blast radius. So if something goes wrong on the database server, it could be server, it could be disk, it could be any kind of exception. If the server is down, then database is down. So that way, because this is one database instance, the whole application is down. What if there is a failover? How do we revive the failover? There has to be some manual process that will revive the failure process to the replication. And how do we scale up if we are in a peak situation where we want to scale up the server, database, and database strategy? Then we have to manually scale it up, add up the configurations, and that's how it is done. So that is also time consuming task. How about the maintenance? If we want to upgrade any uh, uh, versions of MySQL, or we want to upgrade the database server itself or schema, then we need to have a downtime. So these are the situations where we have to have the downtime or kind of failover mechanism. For that, MySQL DB. So if we want to revive, we need to we need to rectify these four boxes. How to fix these? So what database cluster provides us? You see, this is kind of a similar architecture where one application server is connected to one router, which is the orange box in the middle. And this router is the middleware that will be connected to the database cluster. So database cluster means there will be multiple nodes of database, not only single instance, there will be multiple instances of database, as you see in the dark blue box: my cluster 0, my cluster 1, my cluster 2. These are three different instances for the same database. One is the primary, others are replicas. So in case of any failure, we have some backups that will take over right away. So that's why we can easily say on the right side, we have the rectifications, like no single point of failure. So because we do not have single point, so the single point of database, that's why there is no single point of failure. Failover is automatic. What does that mean? If at all there is a failure for primary DB, automatically cluster will decide like which secondary DB should take over, and it will mark that secondary DB as a primary one. So the application will not suffer. Application will have someone that will be responding, probably a downtime of like few seconds. So that's how it will work. then how do we scale out? If you want to scale this cluster from 3 to 5, 5 to 7, 7 to 11, or any number of instances, we can just talk to the database cluster manager, and that cluster manager automatically adds new replicas that is automatically the replica of primary, so there is no data loss, and that's how we can scale up the database cluster itself down. And then how about the upgrades? If you want to upgrade the system, we don't have to put a downtime on the server side because we have multiple instances. Primary is still responding. We can just upgrade all the secondary clusters one at a time, and that's how we can upgrade all the nodes in the database one by one. So these are the advantage of having database clusters. So how do we measure if database cluster is at a good point or not? If it is able to revive in time, how is it able to revive the failover? So the uh, major units to measure it is RPO and RTO. RPO is a recovery point object. Recovery point object means how far back in time, how far back, like let's say there is a failover. So how far back it can go in the data, like it can recover that much data. So there has to be a sync point whenever database is doing the replication. It is syncing the primary and secondary up to a sync point. After that, there is a gap because it's a async process. So what if the failover happens right then? Then we need to decide how much time or how much longer the recovery failure event is taking. That decides the uh, success or failure of a database cluster. Same thing goes with RTO, recovery time object, means how long is it going to take from the failover to recover the cluster completely. Because if it waits for the longer time, that means we are losing the data, we are losing more data. So the lower the RTO and RPO are, best is the scenario for our database cluster. Ideally, in best case scenario, we want no time recovery and zero data loss. So the orange and the green dots will be right on top of the red dot. That means zero recovery time and zero data loss. And that is practically impossible. Or if we are trying to do that, there are some costs associated around it. We can talk about it in the later slides. So this is the next slide for like how do we design our database cluster. Let's say when we are designing the database cluster, what do we need to keep in mind? So the first thing is node failure. Same thing. It should not be a single point of failure. If a node fails, then that doesn't mean the database is down. There should be someone to take over. So that's the first principle to design a database cluster. Then the storage failure. Underneath, database is all about storing something. So if the storage itself is not working, then there is no point of having the database. So storage, we need to persist everything in a place where we can, save that. It should not be deletable. It should be always recoverable. So storage failure is another prime example. How do we design a database cluster? Network partitioning. We should not have all the nodes on a single cluster, on a single site. So whatever we are, it should be a distributed database cluster. All the nodes of that database should be distributed on a different Kubernetes cluster or different Kubernetes nodes, so that at any given point of time, all of them are not down, and they should be able to connect to each other. That's how they will, do the replication and do the sync process. Then the zone, again, the same thing. If we have multiple clouds, if we have distributed database, then we would like to have all the cluster nodes on a different geographical location so that we can safeguard our data and our database if there is any natural calamity happening. So there could be some technical failures, but there could be some natural failures as well. So if everything is at one location, then it's dangerous and it's quite risky to lose all the data. We want to have everything in cloud at multiple locations. So those are the four major fundamentals or major principles we need to keep in mind while designing the database cluster. So these are the strategies how we can design our database nodes. primary, multi-primary, and shared nothing. I'll talk about it in the next slide with the diagram. So this is the actual database full sketch diagram, and this is also an example of InnoDB cluster. So what's going on here? Because this is a Kubernetes environment, we have on the left side, we have the Kubernetes control plane. That means it's a monitor provided by the Kubernetes that will look after the cluster itself. So MySQL operator is a Kubernetes tool that will do all the orchestration for the database components, for the database the cluster components, which includes router, MySQL nodes itself. It should be backup and then other monitoring things. So everything is taken care by MySQL operator. If something goes wrong anywhere, MySQL operator is the first guy that will be notified, and then it will take appropriate steps to fix those failures. On the left bottom, we have MySQL shell. It's nothing but kind of admin API CLI tool where we can actually connect to the we or MySQL operator can actually connect to the database nodes, and then it can execute any query over there to fix anything manually, or if DBA wants to interact with the database, it's not recommended to log into the database nodes directly. CLI, MySQL shell CLI is the tool that should be used. Now, the main point is the middle section of this diagram. As you have seen, this application microservices on the top, then the middle layer is the router. We can have multiple routers so that again at the router level, it's not a single point of failure. Application is connected to router A, and router B is a backup router, which is also connected to the application and to the cluster. At any given point of time, if the primary router, which is router A, that goes down, automatically within seconds or within milliseconds, the application will connect to router B, which is already connected to the database cluster nodes. So that way, we are reducing the risk of failure at single point of router. Then comes to the database cluster itself. Again, cluster has three nodes here. Primary is my cluster 0, then my cluster 1, my cluster 2 are these secondary nodes. So this is how it will, router A has all the information about all the primary and secondary nodes. At any given point of time, router is sending all the read write queries, everything to MySQL cluster 0. That's where it will do all the executions, and whatever is committed, whenever the transaction is complete, it will acknowledge back to the router, and router will acknowledge back to the application. So that's how it will complete the loop. But behind the scene, what MySQL operator is doing with the help of group replication clusters, it will provide all the information from primary node to the secondary nodes to keep them in sync. And that process is happening asynchronously. So it's not conflicting with the traffic of application to DB, because DB to application to DB connection is happening on a different port, and the group replication is happening on a different port, which is 33061. So there is never a conflict between the replication process and the actual application traffic. So that's how the replication will happen. And then we also have other components uh, uh, for the cluster, which is a backup job. All the nodes, they will have their own PVC, which is called persistent volume, and that persistent volume is the storage unit where databases are actually storing the data, and we can have a backup. That is optional, but that is absolutely recommended feature, that you need to have a backup at a different location other than the cluster. So in any case of calamity or in any case of failure, you're not losing the actual data. Cluster is just a technology. You can bring it up, but if you lose the data, then there is no point of recovering anything. So that's why backup is very important. Other than that, we can also have the monitoring pods here, which is monitored by MySQL operator, that will provide you the information about the like what's happening with the clusters, if cluster state is good, if secondaries are in sync or not, which kind of cluster is primary, which one is secondary. If you want to know all those things, that audit information will be provided by the monitoring pod. So that's how it behaves for MySQL InnoDB cluster. And this is a working solution that is provided by Oracle. So it's actually good to learn about it. And now we have multiple strategies how we can define our database cluster. So in the previous one, you have seen the primary replica and the primary replica asynchronous sync, which is like how it is syncing with the secondary nodes. So in this is about like what's the right scalability, what's the consistency and the failover speed, and what kind of complexity we have in multiple scenarios. If we just have a primary replica and every all the replication is happening asynchronously, then definitely the writes are very fast. So it's a single node write, and all the writes are kind of consistent. Failover speed is in seconds, and the operational complexity is very low because this is straightforward scenario. We have single primary, multiple replicas, group replication is taking care of it. If you see the third row, InnoDB cluster, the same thing. We have single primary, single node primary, and then consistency is very strong because every time router is just connecting to the single node. It doesn't have to talk to multiple database nodes. So that's why the failover is in seconds and the complexity is like medium to low. But what if we have multiple primaries? So if you go back to the original picture, you'll see right now we have one primary, but in case of because if let's say there is some trading application, they cannot afford to have 30 seconds of recovery time. So what they can have multiple primaries. At that time, what will happen? Router will talk to all the primaries at the same time, and all the database nodes are updated with the latest data. So that in case of failure, let's say one primary fails, then definitely all the other primaries are up to date with the data. So within seconds or within milliseconds, they can take over and they can respond to the router with the actual data. So that's how they maintain the uh, low failover or low recovery time scenarios. But the cost of it is very high because the router has to talk to multiple primaries at the same time. Router has to make sure that all the primaries have committed the transaction. If one primary hasn't committed the transaction, so that could be a delay to the whole transaction unit. So that's how it could be a hassle in the operational cost. It could be a it could have high write latency. So those kind of issues or those kind of trade-offs you have to balance, and that's how we need to decide how do we have single primary or multi primary or like mid zone somewhere. How do you decide what is good for your application? So that is dependent on the scenarios what you're looking at. And you can also have semi-sync. Semi-sync means one primary and uh, like out of three nodes there are two primaries and one secondary. So router only has to talk to two primaries, not to all of them. So that's how it's like a mid layer or like mid level compromise. So we'll get good RTO, a decent RPO, and then that's how you can decide based on the scenario. Then what are the major three components of a cluster, like how it works in the background? So we have group replication. Group replication means how the replication is happening between the database nodes. Primary has all the latest information, how we are updating secondaries. So whenever group replication cluster have their own database tables, has its own metadata, the operator is the guy who will command everything to group replication. That primary has committed one transaction and it will assign one GTID. GTID means group transaction ID to every transaction. So that's how they will decide within the secondary nodes whether those transaction IDs are committed on the secondary nodes or not, and they are maintaining the records of table for the same thing. So primary has committed one transaction, it will assign one GTID to that, and then replication process will it will just kick in within seconds. It depends on the loop. It's a round robin loop. It could be 5 seconds. It could be 10 seconds. It depends on the configuration. Let's say it is 10 seconds. So every 10 seconds, whatever transactions were committed on the primary node, with the help of group replication, it will all those transactions will go to secondary nodes, and then it will commit over there. If there is any kind of failure, then there is a lag in the process. Let's say the secondary two is not able to commit all the transactions or few transactions those were committed on cluster 0 and 1. So the MySQL operator will maintain those records that cluster 2 is lagging behind cluster 1 and cluster 0. So that's how it will maintain the record, and that lag should not go very high because it may drop the recovery time for the cluster. If MySQL cluster is not up to date, then it may not be the best candidate to become a primary in case of a failover. So these are the things the cluster has to keep in mind, and that's how all the router will take that information from the MySQL operator. And in case of failover, router with the help of MySQL operator will decide which secondary cluster is highly up to date to be selected as a primary. So that's how the group replication works. And then MySQL operator is also talking to the router in terms of exchanging all the information. You see the ports here, which is 6446, 6447 for read only, and 46 is for read write. So there are multiple ports which router can talk to the primary nodes in terms of read write and read only. So that's how it can also behave like a load balancer. So router is not only a mediator between the application and the cluster, it's also a load balancer which can intelligently, divide the transactions or divide the traffic. If there are only read-only transactions, it can simply go to the secondary nodes, and then it can reduce the traffic on primary cluster 0. If there are many read write transactions going on, then it will have to go to cluster 0, and that's how router can intelligently switch, and it can exchange those information to the operator so that operator can orchestrate or uh, fix the cluster accordingly. So the third component is MySQL Shell, which is again the DBA CLI tool where MySQL router and the group replication executes all their commands to verify the cluster state, what kind of primary they have, how many secondaries they have, out of three secondaries or out of three cluster nodes, how many are connected to the cluster. So those kind of information you can get via MySQL Shell. So how group replication performs the internally, how it performs the replication process from primary to secondary. What it does, it will broadcast the GTIDs, which is the uh, group transaction ID, all the transactions to the secondary nodes on a port which is different from the actual application traffic 3306. So it will broadcast to everyone. Then it will certify whether those transactions are duplicate transactions or they are new transactions. If they are new, then it will commit. If they are already committed, then it will roll back. So that's how it will identify whether it has to commit the new transaction or not to the secondary nodes. And it will just keep on doing it throughout his life because that's the job. So there are certain rules which all the group replication or all the clusters have to follow. It says like write requires a majority of the members to be reachable. That means if there are three nodes in a cluster, then majority means 2 out of 3 has to be up and running. So if it is less than that, the cluster will not respond. It will say that it's not up to the quorum rules. So it will decide that cluster is down, because at any given point of time we need to have a replica. So primary is up. Technically, the cluster can respond, but if there is no replica, if there is no one to have a backup, then whatever you're writing to the primary, that's risky because no one is there in case of a failover to take as a backup. So that's why the first rule is very important. The second one is the same example: three nodes tolerates one failure, five nodes tolerates two failures. Same thing. Majority of the members should be reachable. Then two node cluster cannot survive. Again, for the same reason that there has to be one replica. And that's why if there is no one to record the backup, then cluster will be termed as a failure. That's why most of the time, or all the clusters should be in an odd number of member counts. It should be 3, 5, 7, 11. It can never be an even number of cluster, so that it can like MySQL cluster can easily decide if majority of the numbers are up and running or not. It will never have a conflict. Then the MySQL router failover apps. If 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 we have a failure, if we have a failure on the cluster side, so I'll demonstrate the scenario like what will happen if there is a failure on the DB side or if there is a failure on the router side. Router failure is very easy. If router A goes down, router B will take over, and then behind the scene, Kubernetes will start a new router, which could be router C or router A. If router again, that router goes down, then it will assign the responsibilities to the other one. So that's pretty simple. On the cluster side, there is single primary and multiple secondary. If the secondary goes down, then Kubernetes or MySQL operator will automatically spawn a new secondary node, and it will make sure that new secondary node has cloned all the data from the primary, so that it has all the data up to date. But what if a primary goes down? If a primary goes down, then the MySQL operator and the MySQL router are the first guys that will know about it, because they are polling and doing a lookup to the MySQL cluster every 500 milliseconds. So every half a second, they are polling the cluster to check the health, to check the availability of all the nodes, and that's how within half second they will get to know if the primary is down. So what will happen if the primary is down? So if the primary is not there, MySQL router will inform it to the operator, and then operator will look into it. Operator will see what's wrong with it. Meanwhile, it will choose one secondary node to make a new primary. It depends on the state. If they both are up to date with all the latest data, then it will randomly choose one. Let's say it will choose DB node 2 to become the primary, and then DB node 3 will still be the secondary node. That's how it will immediately connect DB node 2 to the router A, so that it will respond to the application traffic. Behind the scene, it will rectify or try to do the root cause analysis for previous primary node A. What's wrong with it? If it is able to fix it, it will try to fix it. It will take the help of all the metadata from the matrix audit data. It will try to contact to Kubernetes if that is something which is in reach of Kubernetes or MySQL operator. It will fix it. Otherwise, it will just create a new node in place of node 1, and it will kill the DB node 1. If that itself is not possible, then it will flag one kind of exception to the logs, and that's how it will say that okay, primary like there is something severely wrong with the primary one, so we cannot put it on. But most of the time, operator will be able to bring up a new node and will make it a new secondary. So that's how it will fix the failover scenario on the cluster side. Now, what's the usage of Kubernetes? Why do we need to have Kubernetes here? Kubernetes certainly chimes in with the help of, it will create all the pods, all the containers with the help of MySQL operator. So that's why it is providing a self-healing nature to the clusters. If something goes wrong, it will either restart the container, restart the pod, or it will just recreate a new cluster itself without having any manual intervention. Then it is declarative and GitOps. What does that mean? Means like we have seen there are so many components on the database cluster, but everything is one GitHub chart, Kubernetes Helm chart in the GitHub. So just one Helm chart can define everything for the cluster. So it's easy to maintain and it's declarative. We can define all the variable parts in the properties. So it's highly configurable, and that's how it's just a single chart which is easily manageable via GitHub. Then we have rolling upgrades. What if we want to upgrade? It's not a complete downtime. In fact, there is a zero downtime if you want to upgrade the cluster. With the help of Kubernetes, because we have Docker images, we can just upgrade one node at a time, and then accordingly we can one by one we can upgrade all the DB nodes subsequently. So that's the biggest advantage of having database cluster. There is no downtime. Application will not suffer. And then you may upgrade your schema, you may upgrade your database version, anything, and that's it. What what are the advantages of cloud? So the cloud advantages are, the first thing is multi-AZ. Multi-AZ means we have multi-cloud capability. If you can have that, that's the biggest advantage and uh, 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 um, biggest boon to have your database as a recovery point. So if your database or your actual data is at a multiple cloud at multiple locations, so you don't have to worry about it. Like your pods or your data can go off if there is a site failure. So you can also apply the pod affinity rule here, which says that similar kind of pods should not be at one side. So if you have multiple layered cloud, you can define or distribute your pods accordingly in multiple locations. Again, for the durable managed storage, so similarly, we can distribute our persistent volumes to the different geographic locations based on that multiple location cloud, the regional cloud. Then we can also have portable no lock-in, because our data is actually detached from the Kubernetes or the cluster layer. The database is just a technical aspect of it. Data is the actual asset. So if data itself is on a different layer, so we can at any point of time we can detach the data, we can detach the database, and we can have a different database to work with the same data. So that's how it's like a portable plugin kind of feature with the help of cloud and Kubernetes. That's very easy to manage. How does it recover from a failover? I talked about it earlier. If a primary dies, then the MySQL operator will detect, and then based on the detection, it will elect one primary from the secondary nodes, and the router repoints to that within half second, and that's how it will assign the new secondary, which is a new primary, to the router node, and then services will restore within 10 to 30 seconds. Why it is 10 to 30 seconds? Because even though a router has determined within half second that the primary is not responding, but there are few background things that MySQL operator has to perform in the database. It has to make sure that it is putting up all the tags, all the metadata fields to the database tables, so that it will maintain the database. Apart from MySQL, so MySQL is not the only way to have database cluster. There are multiple ways, multiple technologies available in the market to have MySQL or to have the database cluster. The first one is Postgres with the help of Petroni or Galera operator. We can have this similar kind of structure. The fundamentals and basics are the same. It's just a technology. We are replacing the MySQL cluster with the Postgres SQL, or it could be any other uh, technology. But the concepts are same: multi-primary, single primary, asynchronous, and the Kubernetes. So those fundamentals still remains the same. The other example is Percona PXE operators with the cloud native PG. This is good to have for cloud native operations. Then for distributed scale out SQLs, we have Vitess and Cockroach DB. So I highly recommend to go through these different clustering mechanisms, or you can try any of those, and you can see what's the actual difference. And yeah, that is all from my side. If you have any questions, let me know. Are you there, Ivan? All right. If there are no questions, thank you.